Okay, great, Ross. Now we're just looking at that example as we discussed before. And I want you to take note. You'll be given or presented with a question as you have the empirical. I just took the question that we had before, this question, and I just put it down there. Now, the best way to think about it, especially at a beginner stage, is to make sure you put your powers, whether you actually write them out or you do it mentally. Just make sure that you can actually see that stuff there, because as a beginner, you would need to see how to manipulate the powers and how the results come about. But again, it's going to come back to, let me just put this on here, the conclusion that we came up with from the last video, this here. So those two are literally, we're going to apply what we have in that box there on those last two. The one with the power x to the power 1 and the one with the power x to the power 0. And just as a addition to the number 2, because for the number 1 I did show you what it means graphically when you have y equals to a constant number. Now remember what this means for you when you have y equals to ax. This is the same as you having y equals to mx plus c. And the last you saw this was when you were dealing with a straight line. Now, regardless of the type of line that you have, as long as it has both x and y, it means that it's going to be slanting. And the meaning that it's slanting, whether you take it from here or from here, the gradient is always going to be the same. The gradient is always going to be the same. That's the reason why if you differentiate y equals to ax, this type of a function, you will always come up with a constant, like we have there. So the gradient of a straight line, as presented by this straight line, but which is sloping, will always give you a constant. We already know that because that's why we have y equals to mx plus c. And this is always going to be the gradient throughout. And then the y equals to a, again, is still a straight line, but which is forever horizontal. Now for this one, we say regardless, the gradient is always going to give us a 0 because it's horizontal. Because gradient is actually a measure of how much a line is slanted or sloping relative to a horizontal surface or horizontal line. So if the line is already horizontal, it means that there's no slope where there's parallel or on the line, then consequently the gradient is going to be 0. Now reverting back to what we're doing here. For this one, I will just rewrite this for x cubed plus 2x squared minus 3x to the 1 plus 2x to the 0. And I'm just going to show you the first procedure, remember this, and then the second procedure. First procedure, second procedure. First procedure, second procedure. First procedure, second procedure. So this is what goes on in your head as you get accustomed to differentiating. You don't necessarily need to show those arrows or the -1, but you may do that at the beginning until you can become so used to it that you don't need to show it every time. So this will end up giving us 3.4x to the power 3 minus 1. I'm just going to show everything for now. 2.2x to the power 2 minus 1. My bad there. 3. The 1 comes down first. 3x to the 1 minus 1 plus, so let's start with the 0 here, 2x to the 0 minus 1. And at the end, what we end up with is a 12x to the power 2 plus 4x to the 1 minus 3x to the 0 plus 0. That's why the last time we said we shouldn't really bother with the x minus 1 there, with the 0 minus 1 there. So effectively, this leaves us with a function that is 12x squared plus 4x minus 3. Is that okay? So this is going to be our derivative function, where if we want to find the gradient of this particular function at any point, we take the x-coordinate of the point, we input the x-coordinate into here. That's why it's in terms of x. And then the output is going to be the gradient of this function here at that x coordinate. That's essentially what it is. So this is what we call the gradient function. So it's still a function because it's forever changing, like we said in the past few videos. But then it allows us or affords us the opportunity to be able to find the gradient at any particular point. And I think you'll see this as we begin to apply differentiation on trigonometry functions, on logarithms and stuff like that. Then, it'll all begin to make sense as to why we need a graded function as well. So I'm not sure if there might be any questions on this, but I'll just do another example and then we'll close this video. So let's say we have something this simple. As per the usual, put my silent 1 minus 1 mean, and then I put my silent x to the 0, like that. So my answer is going to be, my 5 comes down first, dot 6, x to the 4, now I can afford to write that, minus 4 dot 12 x to the 3 plus 1 dot 2 x to the 0 plus my 0 dot 3 x to the minus 1. And the final answer is going to be a 30 x to the 4 minus 48 x to the 3 plus 2. Well, we won't even write the x because it's x to the 0. And the other one, this is going to be equals to 1. And this, as a whole, is going to be equals to 0. So this is going to be our solution. I don't know if you have any questions. Notice how we had to learn the basic differentiation, or rather the differentiation of the basic term y equals to x to the power n for us to be able to deal with anything of the sort. Now, we are not always going to get this type of a function. Sometimes we get functions with brackets or polynomial functions or repeated brackets and so on. Now, the next video is going to tackle how do we deal with differentiation of repeated brackets, which is again another I think classical that is used in exam papers, alongside of course this polynomial type of a function. So I think for this polynomial type, this is essentially what you expect to get. You can even get your powers as fractions. Again, as long as you know your fractions, you can always subtract your ones and you'll still get your final solution. I think we'll see those as we look at exam papers. But for now, this is as much as you can ever get. Now we focus on in our next video on repeated brackets. Let me see you in the next video.